Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon, everyone. So we're now happy to hear the second installment in the talks this week, and we'll hear about the Talagrand's convolution, conjecture, or regularization of L1 functions. Please, Ronen.
Thanks. Okay, so yeah, this is more or less a direct continuation of James's talk yesterday. And James was talking more about the discrete space, whereas today's talk will focus on the Gaussian version of the conjecture James stated. So just to set up, we're talking about Gaussian space, so Rn with this density, and we consider the convolution operator, which just says take a function, and to evaluate the new function at x, we take the expectation of f at this. This is just a rescaling of x. We add a Gaussian to the point and take an expectation over this Gaussian. So this is just convolution with a Gaussian up to some rescaling. This is sometimes called the Ornstein-Uhlenbeck operator. And another way to define this operator is just to see that this is actually the expected value of f at a Brownian motion at time 1, conditioned on the Brownian motion at time 1 minus t. Okay. And as James mentioned yesterday, this operator admits some smoothing or regularization properties. So if we take a function and apply this operator, we expect it to become more smooth in a sense. And one sense is this hypercontractivity property that just says that if I know that my function f has some LP norm, then for this p and for any t, I can stretch p to some q which is bigger than p, and estimate and have an upper bound for the LQ norm, which is bigger, of course, than the LP norm of a function by Helder, given only that I smooth this function with this operator. Yeah?
So what is the gamma in the LP and LQ?
Gamma is the Gaussian measure. It's LP over the Gaussian measure. And okay, this is by now a very fundamental fact in analysis and has applications to concentration and isoperimetric inequalities. And a question that Talagrand raised is whether, so this is a quantitative smoothing result, but somehow it completely I mean, we can't really say anything if we only know that our function is in L1. But note that even for a delta function, there is some smoothing going on. If I take a delta and convolve it with a little Gaussian, I do get something kind of regular, and it's not clear what the correct statement or the correct quantitative statement is for just L1 functions. And Talagrand asked a very specific question. So the question is the following. Also, James mentioned it yesterday. So let's assume, just normalize our function to have expectation 1. Gamma is a standard Gaussian vector. And we know that, of course, this variable f of gamma admits Markov's inequality. The probability to be bigger than alpha is smaller than 1 over alpha. And what Talagrand asks is the following. Is it true that after I do this smoothing, I can improve over just Markov's inequality by just saying that I get some C over alpha. C depends on this convolution, I mean, how big the Gaussian I convolve with is, but times some function that goes to 0 as alpha goes to infinity. So I just want to get demonstrate some slight improvement over just Markov. And basically the only result, so as James said, the Talagrand asked this in 1989, but in a discrete setting, the only result known in either discrete and Gaussian, more or less, that doesn't just follow from what you get from hypercontractivity, which is not much at all, is a result by these 5 guys in 2010, which basically give a bound that depends on the dimension 2. Now, it seems, as I'll try to convince you later, that half spaces should be the worst examples, the sharp examples in the best inequality you can find here. And I mean, this is a typical thing for the Gaussian measure. Most estimates, we expect them to be dimensionless. So, I mean, this dependence on the dimension is kind of bad. It's also exponential. Yeah.
I see the title, but I hope it's nothing profound there.
Oh, right. So there is also a title, but I'll try to. I hope you'll understand the talk nevertheless.
It's a fixed title, or this changes per slide?
It changes per slide, yes. So this slide's title has the letter G in it. but yeah, no, but it's okay, I guess. You won't miss much. So this is the result James and I show. Basically, it says the following: given a function which I know is not too log-concave, if I consider the Hessian of the log, it's bigger than minus some constant times the identity. A good way to understand this thing is this is a function. If I do some gradient optimization, and okay, if it increases, then it has to keep increasing for a while. The gradient cannot turn from increasing to something that decreasing very quickly. If you imagine a set, then this set cannot be very, very narrow. It can't be that I'm climbing up and immediately climbing down again. Then we have the following result. So we assume that the expectation of f is 1, but if we take the expectation of f restricted on some level set of this sort, somewhere between some value s and 2s, then this is not only smaller than 1, but it's smaller than something going to 0 as s goes to infinity. So basically what you should imagine is that such functions cannot have constant mass on a very high level set. It cannot be that half the mass of the function is between 1 billion and 2 billion. Okay, it has to be pretty small on every such multiplicative scale. And
you put 1/7 just in case you made a calculation error?
No, this is just the log. It's so the power here doesn't matter. Okay, the focus of the lecture is to demonstrate little of 1. So
you didn't want to have an s there as well?
Where?
There's an s on the left because f is s.
I'm not sure I understand the question.
F of gamma is s in this. Right.
Yeah, f of gamma is typically s. And okay.
I mean, Markov's inequality would give you a 1 over s, right?
No. So this is just.
Have the f. Okay.
Yeah. This is just without this. This is just 1. I restrict it to a level set. It becomes little o of 1. And I claim that this is equivalent to an improvement over Markov's inequality. And the reason is that I can just say that, okay, so I guess this thing is more or less S, because I restricted to between S and 2S. So this means that S times the probability that f of gamma is between S and 2S is little o of 1. So if I move S to the other side, then this is little o of 1 over S. And then this just means that the probability that f of gamma is bigger than alpha, or, okay, some alpha, is just the sum. K goes from 1 to infinity. The probability that f is bigger than in alpha times 2 to the k to alpha times 2 to the k plus 1. And by using this thing is smaller than 2 to the minus k times little o of 1. And then I sum them all up and I get 1 over alpha little o of 1. Okay, so this is, and also the other implication is pretty easy, but we'll just need this one together with this, which I'll explain in a second, to show that this is actually stronger than the question that I introduced earlier. So what else do we need? So we know that this implies something better than Markov. And I claim that this is implied by taking the convolution with something. So know that everything that's convolved with a Gaussian is just a mixture of translated Gaussians. Every translated Gaussian is just an exponential function times the standard Gaussian, right? And basically a mixture of exponential functions, it's known to be a log-convex. This is called the Arden's theorem. It's just, basically in this setting, it's just Cauchy-Schwarz. So it means that, well, everything convolved with a Gaussian cannot be too log-concave, and we have exactly this condition. All right. So, okay, this is a bit annoying already, but so let's go over an idea for how one could prove such a thing. Let's, first of all, so we had the Gaussian measure gamma, and let's now define a new measure which is called mu. So it's a new measure mu. Define just f d gamma. We change the measure with f. We fix some big value s. Let's just imagine this is 1 billion. And we consider the level set corresponding to s. So all of this E will be all the points where f is between s and 2s. And what we need to show is basically that this measure mu, which is a probability measure, cannot have a constant mass over this level set E. So how can we try to prove it? What I'm going to do is I'll try to take E and perturb it in a way such that I'll try to discover new points. Let's say that S is 1 billion, so E is where F is between 1 billion and 2 billion. I'll try to perturb E to get to a new set where the values of F are between 2 billion and 4 billion. And I'll try to find another perturbation where the values of F are between 4 billion and 8 billion. So I'll try to find some sequence of sets E1, E2, etc., that are disjoint. They correspond to different levels of f. But if I manage to find the super constant number of such sets whose measure is roughly the same measure as that of E, it will contradict the fact that the measure of E is constant, right? Just because the integral of mu is 1. So what's a natural such construction to do? So let's take a point x in E and just follow the gradient. I'll look at the gradient of the logarithm of f in this point. I'll normalize it somehow, and I'll just take delta times this thing to get to some point y. Now, remember this property of f, that if it's increasing, it cannot begin decreasing too quickly. This exactly says that if I take the Taylor expansion of the log of f, then the log of f at y is at least this thing. I mean, the log of f at x, which we assumed to be s, plus this delta. This is just, we take the gradient of the log times this. This is exactly 1. Plus something which is small if delta is not too large. It's small if delta is small relative to this thing.
Yes, you need minus. I mean, okay, is that
yeah, well,
minus?
It's actually minus, but it's big O, so absolute value of this. Yeah. So it cannot, the second order cannot contribute too much. Now, for those of you who are familiar with these things, this thing is usually rather high. This is the expectation of this is the Fisher information. So we might, it's not important if you do not understand it, but there is an obvious reason to expect for this thing to be small. So basically, the only missing ingredient here is, so we do know that the values of f here will be rather large if delta is not too big. But we don't have any idea as for what the Gaussian measure of this set is. Maybe we took the set E and the gradients look like this, and this E1 already looks like this. I have no control at all over the measure of this perturbation. So we have to try something more clever. And what we're going to do is the following. Instead of perturbing the point x, we'll take a Brownian motion which ends at x, and we'll perturb this Brownian motion in an adaptive manner. So this has to do with what James talked about yesterday. And basically, the main tool I'm going to need in order to estimate my new sets is called Girsanov's theorem. So let's take a few minutes to understand what this thing means, what this thing says. So we have a Brownian motion. We consider a standard Brownian motion Bt. And to each point at Bt, we add some drift V sub t. So you can think about this drift as just a jump that's predictable, so we know exactly which way we're pushing the Brownian motion given the past, and we get this new process Wt, which is just Bt plus the drift. And Girsanov's theorem says that the following. So if we consider Bt as some distribution over the space of paths, then there is an explicit change of measure between Bt and Wt. Namely, if you take this distribution and multiply it by this change of density, then Wt becomes itself a Brownian motion. Let me try to explain to you why this formula makes sense. So if we just think of Bt as distinct Gaussian jumps, then one Gaussian jump with a drift v can be imagined like this. So it's, I guess, this is the density up to some normalizing constant of a Gaussian, which we just translate in the direction v. But this is actually, this can be written like this. So it's e to the minus w square over 2 plus w dot v minus v square over 2. And if we think as b, which corresponds to bt, as just w minus v, then this dot product is just b dot v plus v square over 2. So what we get is the following. We get e to the minus w square over 2, which is just the Gaussian density, times e to the b dot v plus v square over 2. This is all of these together, which means that if we multiply by the inverse of this,
Half on the plus, maybe the half is, the plus has no half.
sorry, v square, of course. Yeah.
But
So we see that basically w is a Brownian motion if we only change of measure, apply change of measure, which is the inverse of this. But if you look at this, this is exactly this formula, only we're multiplying many, many infinitesimal guys like this, right? We're just summing up b dot vt and minus 1/2 vt square. So you can also, for to get some intuition about this, you can think as just, so if v points in one direction, in order to make my thing a Brownian motion again, I want this thing to be large. I want my bt to cancel out this drift. Okay, so this is Girsanov's formula, and what's really nice about it is that it implies more or less the following thing. It says that if I have some set in Gaussian space such that, okay, can you see what I'm doing here? If I have a set in Gaussian space such that I can take a Brownian motion and force it to go in this set without applying too much of a drift, then basically this change of measure is not too large, which means that the Gaussian measure of this set cannot be too small. So it's a very nice way to lower bound the Gaussian measures of a set. I just have to construct some drift that goes inside it, which is not so too strong. Note that it's very important for this drift to be predictable. It cannot just do something that relies on what happens in the future. I cannot cheat. Okay, so this is Girsanov's theorem, and the next thing I want to define, or actually remind you from yesterday, is so-called Vollmer's drift. So this is the particular process Vt that James defined yesterday. I'm going to write these formulas because I need them for later. So again, I have the Brownian motion Bt, and I define the process Wt with this equation. dWt is dBt plus Vt dt. I take just Brownian motion plus this drift increment, where Vt is the following. It's the gradient of log of P1 minus Tf at the point Wt. So this is exactly the formula you saw yesterday, which, okay, so I guess you remember we had the set E, and we wanted to go in the direction of the gradient of the log. This drift doesn't exactly go in the direction of the gradient of the log of the function, but it somehow goes in the direction that it expects the gradient to be at time 1, right? So that kind of makes sense. Moreover, if we define mt to be just the expectation, well, the convolution of f with the Gaussian at our current point, which means this is more or less what we expect the value of f to be when the Brownian motion reaches time 1, then this is going to be the only heavy calculation done in this talk. So I'm going to go over this quickly. If you don't understand it, it's not so important. I'm going to give you an intuition about what's going on here later. Basically, if I differentiate this process mt, I just differentiate this formula. I get the partial derivative of this with respect to t. And then, because Wt is a diffusion, I get the Laplacian of this thing. It's not hard to see that these two things exactly cancel out by the definition of Pt. And then I get the two terms that are a result of basically where Wt is going. So I get the gradient of this dot dWt, which is exactly these two terms. And if I take the logarithm on both sides and use Ito's formula again, I get that d of log of mt is exactly this thing. And if I go to the previous slide for a second, you see that I have exactly the same formula in Girsanov's formula. So what does this mean? Let's take t equal to 1 here. I get this formula. And it means, according to Girsanov's theorem, that Wt is a Brownian motion under the measure whose density is 1 over f of 1. This exactly means, to put it differently, it just says that Bt is distributed according to the Gaussian measure. Wt is distributed according to mu. Basically, f of Wt times the Gaussian measure. So James already kind of proved this yesterday in the discrete setting, that this drift Vt exactly gives us the terminal distribution of f. And this is a proof of this thing. So somehow this drift is very, very natural. Also, there's this minimality thing that James talked about yesterday that's going to somewhat help us later. So, okay, so now we have a very strange way to recover this distribution mu, this fd gamma. And we can finally try to understand how one can perturb this thing. And the perturbation will be the following. So we fix a parameter delta, which you should imagine as the delta we had before. In the end, we'll consider multiple values of delta, which will give us many different perturbations of an initial set. And now we take this process Wt and we add some extra drift to it. So dxt delta will be dbt plus 1 plus delta Vt dt. So this is the sadism that James talked about yesterday.
I can't read this, so if you could.
What?
Can you use a different pen?
Yeah, sorry. I have a different chance. Yeah, so. So this is exactly the sadism that James talked about yesterday. Wt is the process dt with some pain induced. We give it some, we push it in some direction, and it suffers a bit or exactly enough to get to the distribution of f. And here we're being really sadistic. We give it even more pain than what we need to get to f. So basically, you can imagine, so if we have the Gaussian measure, this is the origin. We have some set, and we have some drift that we have to apply in order to get to this set. So now we do some overshooting. We give a little bit more of this drift. So, okay, I guess this picture was pointless. And now I want to try to analyze the change of measure that this process induces using Girsanov's formula. So let's see. Girsanov's formula tells us the following. I have an exact formula for the change of measure from the measure according to which B is a Brownian motion. So maybe I'll actually draw a little thing here. So we have the following processes. We have the process Bt, Wt, and Xt delta. This is a Brownian motion This is a Brownian motion with the measure P. This is a Brownian motion with the measure Q, and this is a Brownian motion with the measure Q delta. And we already saw, okay, so I just plug this thing into Girsanov's formula and I get this. But remember that if delta is 0, then what's written in here is exactly the change of measure between Q and P. So, sorry. So I can just factor out this 1 here and 1 here, and I'm only left with the delta terms, which basically says, okay, this is the energy I have, this is the measure I'm losing by pushing Bt into Wt, but I'm going to also lose the energy of this push. Now, I want to somehow approximate this thing. If we look at it for a second, this thing, so the variance of an increment of this process is exactly Vt square, right? The variance of Vt dBt is Vt square. And here we have the integral of Vt square. So we know that the variance of this thing is basically this. So the standard deviation of this thing, which is a martingale, is much smaller than this, which suggests that maybe this whole term can be just neglected. Moreover, if delta is small, then, and let's say that it's little o of 1, then this delta square, let's also neglect this.
But the energy small, I missed that. So the integral of Vt squared is small?
No. Actually, the integral of Vt squared is super constant, because we know, if I go back to the previous slide, that log f of w1, given that f has large value, so this is large, meaning that this is much smaller. This can be neglected. Okay?
So that's large because
the variance of this is this.
Yeah.
Typically, it's
right,
not.
but the whole thing is large because the left-hand side.
Right, exactly. Okay, thank you. Yeah, good point. So, right, so I'm going to neglect this thing, and roughly I'm going to say that the only thing I'm paying to change the measure between this set E and E delta is something like this, e to the minus delta times this energy. And this is given that delta is small enough. Forget this exact quantity.
Why can you restrict to small deltas? I thought that in the end you want to have these disjoint cells.
Right. So here, I mean, the scaling is different. So it's okay. We'll soon see that small deltas suffice because a little change of delta means a big change in the value of f. Okay. We'll see that actually in the next slide. So at this point, we want to use our Hessian estimate. Remember, we know that the Hessian of the log is not too small. This exactly means that f at the point x1 delta, at this perturbed process, is at least f at a non-perturbed process times, and now here we consider the Taylor expansion of the logarithm. So the first derivative of the logarithm is just v1. You remember that definition of vt was just the gradient of the logarithm. So we get v1 dot whatever the drift was. This is just the integral of the drift. This is just x1 minus w1. Minus, we have this quadratic term that's, well, it's something times delta squared, and this thing is, it's not so hard to see that it won't be so large. Let's forget that for now, and assume that we can just approximate by this thing only. Okay, so this is what we expect to gain in the increment of f by the push. Okay? And at this point, it'll be helpful to recall that the process Vt is a martingale. So this is something James said and did not prove. If I have time later, the proof is just a straightforward calculation, but I'll say something about it later if I have time.
In fact, you did the calculation basically on like 5 slides ago, right? So.
Not that Vt is a martingale. I don't think. Okay. So, okay, what we have is the following. We do this push. We get a change of measure which was equal more or less to e to the z. And we get, right? No. We get a change of measure which is equal to e to the minus w, where this is w. And the gain we have in the value of f is e to the plus z. Okay? The previous slide exactly says that the change of measure is e to the minus this thing. And here we have e to the plus this z.
There's no delta e to the delta z? Or?
Oh, delta. They both had deltas, of course. Thank you. Now, the fact that Vt is a martingale, if you look at these definitions for a second, you understand that the expectation of the difference between z and w, which is what appears in the exponent, is just 0, right? Because okay, I guess for each t, I'm taking the scalar product with v1, but the expectation of v1 conditioned on time t is just vt. So I get that the expectation of this is also the integral of vt squared, which makes sense because recall that I'm pushing in the direction where I expect the gradient at time 1 to be. Okay? This is actually more or less also the explanation why vt is a martingale. Okay. So at least in expectation, this push should, the contribution I get from the increment of f should exactly cancel out with the change of measure. The problem is that this is only true in expectation. I have no idea where the gradient is actually pointing. It could be that I expect the gradient to point over there, but when I get to time 1, it points like in a completely different direction. Okay, so it's not so clear that this is enough, but we can look at this thing like this. So we know that the expectation of f over a Gaussian is 1, meaning that under this measure q delta, the expectation of f of x1 delta is 1. Now, we can instead take expectation with respect to the measure, that makes Bt a Brownian motion. And then we get f of x1 delta times this change of measure, which is exactly what I wrote here. Now, so we know that the expectation of the exponent, basically the expectation of all of this is 1. And the expectation of whatever is in the exponent is 0. This means that the variance of z minus w cannot be too large, right? Otherwise, the e to the z minus w would be more than 1. So as long as delta is not too small, this variance is not too big. And finally,
Delta is not too small. As long as delta is not.
as long as delta is not too large, sorry. This, yeah, which means all our estimates from before hold, yeah. So finally, we can write something like this. The expectation of, so now we consider exactly the same thing as here. So this is just the integral of f with respect to the Gaussian measure. But now let's just restrict to one level set.
It's not log f of w1 there?
Of course, it's log f of w1. Then this should be log. So let's just consider this integral, but restricted to this one level set. So we know that it's at least this thing. We just, again, change this by the expectation. But now, look, so we know that this thing is quite concentrated around 0. We just established that. So even if we restrict to some subset whose measure is not too small, it should still be kind of close to 0, right? So if we, remember, we assume by negation that this whole thing is not little o of 1, it's just a constant. So if it's just a constant, it means that we restrict to something of probability 1 over 10. So this thing cannot be too small under this restriction, which means that this expectation is of the same order as the probability that f of w1 is in this same interval. Just meaning that this thing is pretty close to 1.
Again, log f of w1.
Again, log f of w1. Yeah, sorry. Okay, so this basically is not too small, and then we just get the probability of this. Okay, so let's, I know you're confused. Let's try to understand what we achieved so far. So we consider this bad level set where log f is between 1 and 2 billion, 1 billion and 2 billion, or 1 billion and e billion. We looked at the location of this perturbed process given that W1 was in E. So
now e to the billion, this is the value of essence.
No. No. S is a billion. So we had the Brownian motion that ended up in this set E. We look at, sorry, this is WT. It ended up in E. We look at this perturbed thing, X, so this is W1, this is X1 delta. It ends up somewhere. And what we saw is that given that WT ends in E, the value of f at X1 delta is quite large. It's at least f of WT times this thing. And we also know that z is large, so we know that we actually get some multiplicative gain by going from W1 to X1. And we know that when we integrate over the paths such that W1 is in E, we still get a pretty decent measure. This exactly means that if we look at, okay, so it doesn't, it says something about the measure of paths, but intuitively what it means is that if we look at the set where x delta terminates, given that w terminates in E, then this set has roughly the same measure as the one of E. This is more or less what this equation says. It doesn't say something about, so it says something about the measure of paths that end in this set. But, well, this, the measure of Brownian motions which end here is just the Gaussian measure of this set.
Is this equation also true if the probability is very small? Because I agree when it's
right. So you get some dependence, right? There is when the probability goes to 0, then this estimate goes to infinity somehow, of course. But we're just trying to get a little O of 1.
It's not going to be okay. This probability is not going to be 1 over s in the end.
No.
No. It's going to be something like 1 over log s to some power.
But the point is, when you change the measure, you get rid of this 1 over s. So now 1 over s, yeah, like epsilon over s is now epsilon, right? So
yeah. But you agree that this contradicts just the constant. Of course, you have to do something much more delicate to understand exactly how the dependence works. Okay, so now we know that Z is more or less W, which is more or less this thing. And recall that f of W. So we had this formula that says that f of W1 is roughly this thing. So we get that this thing is roughly log S. And if we plug the fact that Z is roughly log S into this formula, we get that f of x1 delta is S, but we get some multiplicative gain like this. So as long as delta is bigger than something like 1 over log S, we already get some multiplicative constant gain. And that's almost it. So we know that this thing is in a set where the values of f are bigger, but using Markov's inequality, we can also, this is pretty easy, but I'll skip the details. We can also know that the values of f cannot increase too much, just because the change of measure wasn't too small. So it cannot be, I can't just gain probability from nowhere. So just by Markov's...
Is probability 1 or
what's that?
It's larger than s times 1 plus 2 delta, that's with probability 1?
No. So both of these things are only with probability. So this depends on this z, on this variable z, which just typically is close to w, but not deterministic. So for most of the paths that end up here, the value of f here is indeed different than the values of f here. And, well, as I said before, by assigning now to delta different values taken from a suitable arithmetic progression, I can take this level set E and discover new level sets, E1, E2, E3, so E delta 1, E delta 2, E delta 3, such that they are all disjoint and they all have a measure comparable to that of E, and this exactly demonstrates that mu of E is little o of 1. How much time do I have? I have to finish at 4:30 or now?
4:35.
Ah, wow. Okay, so I won't even need so much. Okay. Yeah. So this exactly means that we created these sets, and this kind of finishes the idea of the proof. And if we optimize over everything, we get that actually this is the dependence we get up to a log factor. Okay, so I'll just talk about some possible future directions of research related to this, and then maybe I'll try to explain why VT is a martingale, because I think it's really a central point of what's happening here. Okay, so first of all, so the theorem so note that the main theorem didn't have this convolution in it. It just talked about functions which are not too log-concave. And these functions they can be defined on any basically Riemannian manifold, and even they make sense on Riemannian manifolds with densities. So maybe it's reasonable to expect that this kind of result holds in like a more general setting of spaces satisfying this Bakriya-Marie curvature dimension condition. Okay, so I guess if you don't know what this is, just, okay, a natural question. Does this thing hold on the sphere, for example, or on any positively curved Riemannian manifold, hopefully?
What's the measure?
So just the measure you get from the Riemannian metric.
Volume measure?
On the sphere, it's even volume measure.
Yeah. Just
You had Gaussian measure in Euclidean space.
right, but if it's a compact,
Okay.
yeah. So positively curved is
Strictly positive.
yeah. Strictly positive.
No,
yeah.
no. Non-negative.
Right, non-negative and compact. Right.
Compact.
Yeah. And I guess like the correct normalization. So you will need to know something about the diameter. I'm not sure.
I don't even think you need compact. I mean, we're talking about a question, which is
Finite volume?
Yeah.
Why finite volume?
So what's the measure?
You need a probability measure, and it should be stationary for some kind of diffusion process. And then you need non-negative.
For the Brownian motion on the manifold. So just the.
Oh, one.
Yeah, that's, I don't know if it has like it's the usual measure on a Riemannian manifold, on a compact Riemannian manifold.
Okay.
Yeah, okay. So all I'm saying is maybe this is like this type of inequality holds in a more natural setting. Okay, one obvious direction, we get log to the -1/6, and well, at least it's natural to expect that one-dimensional thing will demonstrate what the sharp dependence is. And for just translations of the Gaussian, we get log to the -1/2. So is this the correct exponent?
This is like an optimal form, but really just mean f is constant on a half space.
Yeah. Okay. Of course, there's the discrete version of the question that James mentioned yesterday. So the convolution operator is just re-randomizing some bits on the cube and taking expectation. And the main reason this proof fails there is that we cannot just take a small perturbation of a point on the discrete cube. So we can consider these two processes, these two analogs of BT and WT, which James described yesterday, but it's not really clear. So we can basically, okay, it's not clear what this point, x1 delta, should be, right? Maybe you can get some random point that, but okay.
So for if n is not too big, you can apply this previous result of Wolf and friends. And then if n is very big, then the Gaussian thing is a good approximation. So shouldn't that give you a little O
If
result?
n is very big, then it's not clear to me
First
why
of all,
the.
the result that he say was in the Gaussian
so-
setting, so it doesn't apply to the cube at all.
So it's, if you look at the cube but fix the dimension, you know, bounded dimension,
Okay.
then
It's true trivially.
it's true trivially. And
Because
if
the
n
tail
is,
can only go up so high.
right.
Right.
And if n is very large, then you know the coupling to the Gaussian should.
I don't.
No,
I don't know
this is true under some smoothness conditions of the function. I mean, the function is not.
It's smooth.
It's
because
just
a
no,
convolution.
it's completely false.
Yeah, but not
We're undermining
nearly.
so much analysis of functions on a discrete cube. They don't look, even in high dimensions, they don't look like Gaussian space. They can depend very heavily on a small number of coordinates. Or think about tribes, for
Yeah,
instance.
but again, if it depends very heavily,
Yeah,
then it's back to the.
Well, okay, I guess the type of smoothness it has to. Okay.
That's why I told you tribe. It's a symmetric function, which doesn't look like anything in Gaussian space, right? You can't just go to a subcube. And you know this function well.
So this, for those of you who know how to prove hyperconjectivity using those semi-group proofs, they basically only use the second variation, the first variation of what's happening there. They take the derivative with respect to the semi-group, and what we do here kind of looks also at the second variation. So this, on an intuitive level, when we try to analyze, so when we went from W1 to X1, we had this expected gradient, but we also had to scrutinize what happens with the variance of the gradient. And this can be, this is ideologically, so you have to look at the second derivatives of what's going on. And of course, an obvious question is, does this give anything more? So should I take the 5 more minutes to just talk about this process VT, or maybe we can do it offline?
Yeah, you even have a better, you have the change of measure, so you can do it in one line, right? You know now what the change of measure is.
Yeah, but I don't want to, just the calculation, even I don't understand it. I want, something that actually gives you an intuition of what's going on. Okay. So thank you.
Continue offline. Let's